welcome to this problem walkthrough. Today, we will explore an interesting challenge from problem number 1878, get biggest 3 rhombus sums in a grid. This problem involves working with grids and calculating geometric patterns, testing both your algorithmic thinking and optimization skills. Let's dive in. In this problem, we are working with a 2D grid of integers, where the grid has dimensions m by n, and each cell contains an integer. Our goal is to find the largest 3 unique sums of rhombus shapes that can be formed within the grid. A rhombus is defined by a center cell, specified by its row and column indices, and a distance k, which determines how far the vertices of the rhombus are from the center. The vertices of the rhombus include the top, bottom, left, and right cells, along with all the cells that connect these vertices along the edges. It's important to note that the value of k must ensure that all the cells of the rhombus remain within the grid boundaries. If fewer than 3 unique rhombus sums are possible, we return all unique sums in descending order. Otherwise, we return just the largest 3 unique sums in descending order. The values within the grid can range from negative 10,000 to positive 10,000, which means both very large positive and negative sums are possible. The output of the problem is a list containing the largest 3 unique rhombus sums, sorted in descending order. To better understand this, let's look at an example. In the first example, the grid provided is a 5 by 5 matrix. The largest rhombus sum is 228, which comes from a rhombus with its center at position 2, 2, and a k value of 2. This covers most of the grid and includes values from the center and all its surrounding edges, forming the largest valid rhombus. The next largest rhombus sum in this example is 216, which comes from another rhombus with the same center at 2, 2, but with k equal to 1. This smaller rhombus still includes the center and its immediate surrounding edges. Finally, the rhombus with k equal to 0 is simply the center cell itself, which contributes a sum of 200. Combining these, the 3 largest unique sums are 228, 216, and 211. Another example involves a smaller 3 by 3 grid, where the largest rhombus sum is 20, coming from a rhombus with its center at 1, 1, and k equal to 1. The other 2 sums, 9 and 8, come from individual cells at 2, 2, and 0, 1, respectively. In the final example, we have a grid with only one cell, which means the only possible rhombus sum is the value of that cell itself. Here, the result is 7. This highlights a key consideration: the constraints of the problem ensure that rhombuses must fit entirely within the grid boundaries, and in smaller grids, this may limit the possible sizes of rhombuses. Additionally, values in the grid can be very large or small, so care must be taken when calculating sums. Edge cases include grids with just one cell, grids where all cells have the same value, and grids with values at the extreme ends of the range. These constraints and examples help clarify how to approach the problem effectively. To solve this problem, a brute force approach is the most straightforward way to begin. The idea is to iterate over every cell in the grid and treat it as the center of a rhombus. From there, we calculate rhombus sums by expanding outward layer by layer. For any given side length, we compute the sum of the rhombus perimeter by traversing its 4 edges step by step. However, we must ensure that the rhombus remains entirely within the grid boundaries as we expand it. Once we've calculated the sums for all possible rhombuses, we collect them into a set to ensure uniqueness and then find the top 3 largest values. While this approach is simple and intuitive, it is computationally expensive. For every cell, we attempt to construct rhombuses of increasing side lengths, and the process of summing their perimeters involves repeated computations. In the worst-case scenario, particularly in large grids, this results in a time complexity of O, m n min, them, n, caret 2, where min is n, represents the maximum possible side length. While this method works well for small grids, it becomes inefficient as the grid size increases due to the heavy redundancy in perimeter calculations. An optimized approach can significantly reduce redundancy by leveraging pre-computations of diagonal sums. Here, we pre-compute 2 auxiliary matrices, diagram 1, which stores the cumulative sum of values along the downward right diagonals, and diagram 2, which stores the cumulative sum along the upward right diagonals. These pre-computed values allow us to calculate the perimeter of any rhombus in constant time for each layer expansion. The process begins by constructing diagram 1 and diagram 2 in O(m*n) time. With these matrices ready, we iterate through each cell in the grid, attempting to construct rhombuses by determining which side lengths fit within the grid boundaries. For every valid rhombus, its sum can be calculated with a few simple arithmetic operations using the pre-computed diagonal values. To track the three largest unique sums efficiently, we can use a sorted set or a priority queue. This approach improves the time complexity to O(m*n), where the pre-computations dominate the cost for smaller grids, and the rhombus generation becomes the primary factor for larger ones. By avoiding redundant edge traversal, this method becomes scalable for larger inputs. The optimized approach has several advantages. First, it eliminates redundant computations by directly utilizing the pre-computed diagonal sums, which reduces the time spent on summing rhombus edges. This makes it highly efficient and capable of handling larger grids effectively. However, it does come with trade-offs. The implementation is slightly more complex due to the need for pre-computations, and it requires extra memory to store the auxiliary matrices diagram 1 and diagram 2. Alternative approaches, such as divide and conquer, are not suitable for this problem due to the irregular shape of rhombuses, which makes it challenging to break the grid into smaller, manageable subproblems. Dynamic programming, while theoretically feasible, doesn't offer significant advantages over diagonal pre-computations and would involve more complex state management, making it less practical. Overall, the optimized approach balances efficiency with a manageable level of complexity, making it the most effective strategy for solving this problem. The chosen strategy for this problem is the optimized approach that utilizes diagonal pre-computations. The key insight here is recognizing that rhombus perimeters can be computed in constant time by leveraging the cumulative sum stored in diagram 1 and diagram 2. This eliminates the need for redundant edge-by-edge traversal, dramatically improving the algorithm's efficiency. This method strikes a good balance between performance and implementation complexity. While the diagonal pre-computations require additional memory, the time savings they provide make the approach scalable for larger grids. In comparison to brute force, this method is exponentially faster for grids with larger dimensions. Other alternatives, such as divide and conquer or dynamic programming, either fail to address the problem effectively or introduce unnecessary complexity without substantial performance benefits. By opting for diagonal pre-computations, we achieve an optimal trade-off, a solution that is efficient, scalable, and practical to implement, making it the best choice for tackling this problem. In this problem, we are working with a 2D grid of integers, and our goal is to find the three largest unique sums of rhombus-shaped regions within this grid. A rhombus is essentially a diamond shape, centered on a grid cell, with its edges extending symmetrically outward. To tackle this, we need an efficient algorithm that can handle rhombuses of all valid sizes and ensure the sums are unique. The first step in the algorithm is input validation. We verify that the grid is not empty and has at least one row and one column. If the grid fails this check, we simply return an empty result. Next, we define key concepts. A rhombus of side length k has edges that extend outward from a center cell 4k steps in 4 diagonal directions, and the sum of the rhombus is calculated as the sum of all the cells along its perimeter. To compute rhombus sums, the algorithm iterates over every cell in the grid, treating each cell as a potential center of a rhombus. For each center, we calculate rhombus sums by increasing the side length k until the rhombus exceeds the grid boundaries. Calculating the perimeter of a rhombus involves several steps. Starting at the topmost point of the rhombus, we traverse diagonally down left, then down right, followed by up right, and finally up left, returning to the starting point. This traversal ensures we capture all perimeter cells while maintaining the rhombus shape. It's critical to perform boundary checks during this process to avoid invalid computations if the rhombus extends beyond the grid. After calculating the sum, we store it in a set to automatically handle duplicate values. Finally, the unique sums from the set are converted into a sorted list, which is returned as the result. A few key insights help optimize our approach. First, the symmetry of a rhombus allows us to break its perimeter into 4 symmetrical edges, which minimizes redundant calculations. Second, boundary checks are essential to ensure that rhombuses with large side lengths do not exceed the grid dimensions, saving unnecessary computations. The use of a set is another important feature, as it automatically handles duplicate sums, simplifying the task of identifying unique values. Additionally, there are optimization opportunities such as pre-computing prefix sums for rows or diagonals. These pre-computations can significantly speed up the process of calculating rhombus sums, especially when dealing with larger grids. To implement this algorithm effectively, we rely on a few key data structures. The grid itself is represented as a list of lists, which stores the input values. A set is used to store unique rhombus sums, ensuring that duplicates are eliminated automatically. During computation, intermediate variables are used to track the current center, the side length of the rhombus, and the accumulated sum as we traverse its perimeter. These structures and variables work together to ensure the algorithm is both efficient and easy to manage. Analyzing the algorithm's complexity gives us a clearer picture of its efficiency. For time complexity, we iterate through each cell in the grid, and for each cell, we compute rhombus sums for increasing side lengths until the rhombus exceeds the grid boundaries. If n is the number of rows and m is the number of columns, and the maximum side length is the smaller of n and m, the overall complexity is approximately O, n asterisk m asterisk min, n, m. For space complexity, the dominant factor is the set used to store unique sums. The size of this set depends on the number of unique rhombus sums, denoted as U, giving us a space complexity of O, U. To ensure the algorithm handles all scenarios, we must consider several edge cases. For a single-cell grid, the only possible rhombus is the cell itself, making the sum trivial to compute. In non-square grids, where the number of rows and columns differ, the algorithm must still handle rhombuses correctly. For large grids, performance optimizations become critical to manage the increased computational load. Finally, grids with negative numbers must be handled appropriately, as rhombus sums may result in negative values. Accounting for these cases ensures the algorithm is robust across a wide range of inputs. Thorough line-by-line explanation with detailed reasoning for each part of the code, 2 to 3 minutes, approximately 300 to 450 words. Here, we begin our Java implementation of the problem. First, we import the necessary packages, including java.util** for data structures like set and list. In the getBiggest3 method, we start by determining the dimensions of the grid, which are the number of rows and columns. We initialize a hash set called uniqueSums to store rhombus sums while ensuring uniqueness. Next, we calculate the sums for zero-size rhombuses, which are simply the individual cell values. This is done with a nested loop iterating over all grid cells, where each cell's value is added to uniqueSums. Following that, we consider rhombus sizes greater than 0. For each size, we iterate through potential center points of rhombuses, ensuring they fit within the grid boundaries. For every valid center, we calculate the rhombus sum using a helper method, calculate rhombus sum, and add it to the uniqueSums set. Once all rhombus sums are collected, we convert the set to a list and sort it in descending order to prepare for extracting the top 3 sums. After sorting the sums, we determine the top 3 largest unique sums. To do this, we create an integer array, result, with a length of either 3 or the total number of unique sums if there are fewer than 3. We then populate the result array by iterating through the sorted list and assigning the values to the array. Finally, we return the result array from the method. Next, in the helper method calculate rhombus sum, we calculate the sum of all elements forming a rhombus of a given size, centered at a specific cell, R, C. We start by initializing a variable total to store the sum. The first step is to calculate the contributions from the edges of the rhombus. For the top left to bottom left edge, we loop over the size of the rhombus, adding the corresponding grid values from both the top left and bottom left edges. Similarly, for the top right to bottom right edge, we add the values from the top right and bottom right edges of the rhombus. Since the corners of the rhombus are counted twice in the earlier loops, we subtract these double-counted values from the total. This includes the 4 corners, the top, bottom, left, and right corners of the rhombus, which are at positions R size, C, R plus size, C, R, C size, and R, C plus size. After adjusting for these overlaps, the total sum for the current rhombus is complete, and we return this value as the result of the calculate rhombus sum method. This helper method is crucial because it allows us to efficiently and accurately compute the sum of any rhombus shape in the grid. With this implementation complete, our solution can now handle grids of varying sizes and return the top 3 largest unique rhombus sums. To solve this problem, we start with the simplest case, a grid containing only a single cell with the value 5. First, we initialize the grid dimensions as 1 row and 1 column, and we create an empty set called unique_sums to store unique rhombus sums. Next, since there's only one cell, we calculate the rhombus sum for size 0 at position 0, 0. A rhombus of size 0 consists of just the cell itself, so the sum is simply the value of the cell, which is 5. We then add this sum to the unique_sums set. Because the grid is too small to form larger rhombuses, we skip any further calculations. Finally, we extract the top 3 largest sums from the unique_sums set. In this case, there's only one unique sum, which is 5, so the result is 5. Now, let's move on to a slightly larger grid, a 3 by 3 matrix. We start by initializing the grid dimensions as 3 rows and 3 columns, and we again create an empty set called unique_sums. Then, we iterate over all the cells in the grid, focusing first on the center cell, 1, 1, with the value 8. For this cell, we calculate rhombus sums for both size 0 and size 1. A size 0 rhombus is just the cell itself, so the sum is 8, and we add it to unique_sums. For a size 1 rhombus, we consider the edges formed by the top left, top right, and bottom right cells relative to the center. We ensure to account for any overlaps or double-counted corners, adjusting the totals as needed. Once the calculations are complete, we add the resulting sums to the unique_sums set. This process continues for other relevant cells and rhombus sizes within the grid, ensuring all unique sums are captured. The time complexity of solving this problem largely depends on how we calculate the rhombus sums for all possible centers and sizes. Let's break this down step by step. First, the grid has dimensions of m rows and n columns, so the total number of cells in the grid is proportional to m*n. Each of these cells can act as the center of a rhombus, meaning there are m*n potential rhombus centers. Now, for any given cell to be a valid rhombus center, the rhombus size is limited by the smallest distance to the grid boundary. This maximum size, denoted as k_max, is proportional to min, m(n). Finally, calculating the sum of a rhombus of size k involves summing the values along its 4 edges. Since each edge contributes k cells, the total operations for summing a rhombus of size k is k. Adjustments for double-counting corners are done in constant time, so the overall cost for a single rhombus of size k remains k. To calculate the rhombus sums for all valid sizes at each center, we consider rhombuses from size 1 to k_max. The total cost for one center can be expressed as the sum of the first k_max integers, which simplifies to k_max 2. Since there are m*n centers, the total cost of calculating all rhombus sums becomes m*n k_max 2. Additionally, we need to store these rhombus sums in a set to ensure uniqueness and extract the top 3 largest sums. Sorting the unique sums involves a cost of s*log s, where s is the number of unique sums. In the worst case, s is proportional to the total number of rhombuses, which is m*n k_max. This makes the sorting cost m*n k_max log m*n k_max. Combining the two parts, the overall time complexity is the sum of these contributions, resulting in m*n k_max 2 plus m*n k_max log m*n k_max. In practice, the first term, m*n k_max 2, tends to dominate the overall complexity because summing the rhombuses is the most computationally intensive part of the process. As a result, the time complexity is approximately m*n k_max 2. Turning to space complexity, the grid itself requires m*n space. The set used to store unique rhombus sums can, in the worst case, hold up to m*n k_max sums, as there may be one unique sum for each valid rhombus. Finally, auxiliary variables used for calculations take constant space, so their contribution is 1. Thus, the total space complexity is determined by the grid storage in the set, resulting in m*n k_max. When we analyze the overall space complexity, it is clear that the dominant factor is the storage of the grid in the set of unique rhombus sums, leading to a total space complexity of O(m*n*k_max. Comparing this to a naive approach helps highlight the efficiency of the optimized solution. A naive method would compute rhombus sums by explicitly iterating over all cells within each rhombus, leading to a cost of O(k²) for a single rhombus of size k. Across all rhombuses, this results in a time complexity of O(m*n*k_max3. In contrast, the optimized approach avoids this cubic dependency by calculating sums based on edges rather than all cells, reducing the complexity to O(m*n*k_max2. This improvement is significant, particularly for larger grids and rhombuses. Finally, let's consider the best, average, and worst-case scenarios for this algorithm. In the best case, for a very small grid where m and n are close to 1, the complexity reduces to O(k_max2), since there are fewer centers and smaller rhombuses to compute. For average cases, typical grids with moderate dimensions result in the complexity being dominated by O(m*n*k_max2). In the worst case, when the grid dimensions in k_max are at their maximum values, the full complexity of O(m*n*k_max2) is realized. This analysis highlights how the algorithm scales across different grid sizes and rhombus configurations. When tackling the problem of finding the biggest 3 rhombus sums in a grid, there are several common mistakes to watch out for. First, miscalculating rhombus boundaries is a frequent error. This happens when the rhombus expands beyond the grid's limits, or when symmetry is assumed in rectangular grids where vertical and horizontal dimensions may differ. It's crucial to carefully validate the boundaries for each rhombus to avoid index errors. Another common pitfall is relying on an inefficient brute force implementation. This often involves recomputing sums for each layer of the rhombus instead of reusing results already computed for smaller layers. This inefficiency can significantly increase time complexity, particularly for large grids, and might lead to a time limit exceeded error in competitive coding scenarios. Additionally, overlooking edge cases, such as single-cell grids, non-square grids, or rhombuses with a size of 0, can result in runtime errors or incorrect outputs. Finally, incorrect usage of prefix sums is another frequent source of mistakes. Misapplying this technique, such as failing to subtract overlapping regions properly, can lead to inaccurate calculations, especially when handling larger rhombuses. These issues highlight the importance of both precision and efficiency when solving this problem. Now, another critical aspect is understanding the constraints of the problem. Ignoring constraints like grid size or the maximum allowable rhombus size can lead to unnecessary computations and inefficiencies. Optimizing for these constraints is essential for crafting an effective solution. From an interview perspective, this type of problem is an excellent opportunity to demonstrate pattern recognition. Rhombus problems often rely on geometric properties and efficient sum calculations, and techniques like prefix sums or sliding windows can be powerful tools for optimization. It's also vital to focus on edge cases such as grids with irregular dimensions, grids filled entirely with zeros, or scenarios where no valid rhombus exists, because these are often used to test the robustness of your solution. When discussing trade-offs, start by acknowledging that while brute force approaches are intuitive, they become impractical for larger grids. Pre-computing prefix sums, on the other hand, introduces some setup overhead but can drastically reduce repetitive calculations, making it a more efficient choice. Lastly, clear communication is key during interviews. Explain your approach step by step, beginning with a simple brute force method and gradually refining it to a more optimized solution. This shows both your thought process and your ability to adapt your approach based on input size and constraints. To deepen your understanding, consider exploring related problems that share similar concepts. For instance, LeetCode 304, range sum query 2D immutable, involves efficient sum calculations in a grid, making it a helpful exercise in prefix sum techniques. LeetCode 1300, sum of mutated array closest to target, and LeetCode 1035, uncrossed lines, introduce alternative geometric or numerical concepts that can broaden your problem-solving toolkit. Additionally, LeetCode 764, largest plus sign, is another grid-based problem that involves maximizing a geometric shape, providing a complementary challenge. When looking at alternative approaches to solving rhombus problems, brute force is the most straightforward but also the least efficient. While it's simple to implement and intuitive, its n cubed, or worse complexity makes it unsuitable for larger inputs. A more efficient option is prefix sum optimization, which minimizes redundant calculations and is better suited for large grids, though it does require extra memory and pre-processing time. Another approach, the sliding window or two-pointer technique, offers a space-efficient solution for fixed-size rhombuses. However, its flexibility is limited when dealing with variable rhombus sizes. Understanding these different methods and their trade-offs will help you choose the best approach for any given scenario. Great job! We've covered the key concepts and approaches to solving problem number 1878. Remember, practicing problems like this strengthens your ability to handle grid-based challenges and optimize for performance. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!